Welcome to our discussion on special functions and their graphs. So we're going to look at how to graph and apply some basic functions, including constant ones and power ones. We're also going to look at polynomial and rational functions, and then lastly, absolute value and piecewise defined functions. So let's start with the basic functions, i.e. the constant function, which is a straight line, right? A constant function is something that has a constant slope, and a constant slope is a straight line. Now, normally in mathematics, we call a constant function being a horizontal line because it has the same y value, right? It's constantly at y equals 1 or y equals 2 or y equals 3. But in a business sense, a constant function is any straight line, I guess, that has a constant rate of increase. One that goes through the origin is called the identity function because for every x, you get the exact same y, right? It's basically defined as just y equals x. This is the normal version of a constant function, right? A horizontal one. So that's a slope of 0, and this one would be y equals 2. Functions of the form ax plus b are called power functions, but they have other names. I mean, obviously, if b is a 2, then it becomes a quadratic, right? And we've dealt with quadratics before, or parabola. And then the others also have fancy names, but we can just refer to them as power functions, which is fine. Just know that b has to be greater than 0, but it can be a fraction, right? So this is actually x to the 1/2 power, just like this would be x to the 1/3 power, and so on and so forth. So here's what they would look like, right? There's our parabola, our quadratic, power of 2. Here's power of 3. It looks kind of like a lightning bolt, or basically if you took this half of the parabola and cut it and flipped it down, you'd see that you would get this shape. The square root of x is basically just half the parabola on its side, and then the cube root of x is basically x cubed on its side. So those are the graphs of them. If you have just a basic, right, any of these basic functions where you're only concerned with the first quadrant, which is what we normally are concerned with when we're dealing with real-world applications, because again, in the real world, you can't have negative numbers usually. I mean, other than like owing money, but usually the x-axis represents a number of things like units produced, and you can't produce negative things. So that's why we concentrate on just the first quadrant. So here's our parabola-looking thing, here's our constant thing, here's our other power function, but this would be a power function where x is between 0 and 1. Once you know what a basic function looks like, you can then get all sorts of variations of that function by applying shifts and stretches to it. We're going to look at shifts first, right? And shifts can either be vertical shifts or horizontal shifts. And in fact, the nice thing about math is everything generalizes. Anytime you do anything to the outside of a function, it's always going to affect the vertical aspect of that function. Anytime you do any kind of augmentation to the inside of a function, that's always going to have an effect on the horizontal portion. Right? It's going to affect it horizontally. Now, if we look at this function here, we know that the general function, right, the most general basic version of this is just y equals some function in terms of x, right? So this is our function. This is inside our function, and out here would be outside our functions. So I'll ask you, which of these two letters is inside the function? And hopefully you're all saying h is inside, and then k is on the outside. So that's why when we put an h on the inside, it shifts the function in the x direction. It messes with the horizontal. And when we add something to the outside, it shifts it in the y direction because the outside always messes with the vertical. Now, the inside of the function is always counterintuitive. It goes the opposite direction. So that's why we write the generic function of x minus h. So then it goes it goes h units in the x direction. So for instance, if we start with f of x and then we go f of x plus 3, this doesn't go 3 units that way. It goes 3 units to the left because even though it's a positive number, it goes in the opposite direction. And that's what the minus sign here reminds us, is that on the inside of the function, it acts in the opposite directions. Whereas on the outside of the function, right, so if we added a 5, that's going to go up by 5. So the outside, things that we do on the outside act intuitively. They do what we think they should do. Whereas on the inside, they do the opposite of what we think they should do. Okay, so if we start with the basic function of x cubed, which we know is this little lightning bolt looking function, and then we put a minus 3 on the outside, it's going to shift it down by 3, right? If we put a minus 2 on the inside, remember it's going to go to the right by 2, and then if we do both of them, it's going to do both of them. It's going to go to the right and down. So here's what we can see, right? This shifts it down by 3. This shifts it over by 2. And then finally, both of them over by 2, down by 3. It's just that simple. Don't overthink it. There's really nothing to that. Polynomial functions are just like the power function. They just have a bunch of extra junk trailing on behind it. Now, we describe them with all of this confusing looking jargon, but basically it just means that you have a bunch of coefficients in front of a bunch of powers of x. That's all this means. And instead of giving the coefficients a different letter each time, like make this A, B, C, D, da, 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 we don't want to possibly run out of letters, right, and get all the way down to Z and then be like, uh-oh, we need more letters. So instead, we're just going to call every letter A, but we're going to give it a different, so this is going to be A sub n, and then A sub n minus 1, all the way down to A sub 1 and A sub 0. So the one in front of here would be A sub 2, A sub 3, A sub 4, A sub 5, as we go all the way to the front. So the reason why we use n's is it basically says this can get as big as we need, right? Whatever the power of the function is, right? So if this was to the power of 15, then this is going to be A sub 15. It's technically the 16th one because A sub 0, right? So we have 0 through 15. But we do that so that everything matches, right? So the power of 15 has A sub 15. The power of 14 has A sub 14. All the way down here, the power of 1 has A sub 1. And then this is technically a power of 0, right? Because anything raised to a 0 is just 1. So that's why the x goes away. Has A sub 0. A polynomial function just has one real rule, that the leading term has to be anything other than 0. Because if this was a 0, it would just go away, and then this would become the leading term. And then we would say, oh, well, then we're just now going to call that A sub n, and everything gets shifted down 1, right? And the other thing is, in order to be a polynomial function, all of the powers must be integers greater than or equal to 0. So we can't have fractions, we can't have negative numbers, but we can't have zeros. A power of 0 just means it goes away, right? So at the end down here, x to the 0 just goes away, becomes a 1. And so that's the one where x has a power of 0. Now, a linear function is just a special kind of polynomial function with a degree of 1. That means the degree of the function is always the highest power of the function, which is our leading term here. So this polynomial has a degree of n, and if we let that be a 1, then it'd be a times x, right, to no power, and then it would just be plus this constant. You go, oh, that's a straight line. And then a quadratic function is just a polynomial function with degree 2, because you'll remember that quadratic functions are written as ax squared plus bx plus c. Because we only have 3 of them, we don't go to the hassle of saying a sub 2 of x squared plus a sub 1 of x plus a sub 0. But it's the same thing, right? It's still a polynomial function. It's just we use it so often, and subscripts are such a pain in the butt that with something like this, we're just going to go ahead and let it be a, b, and c rather than a sub 2, a sub 1, and a sub 0. Okay, so once you know these families of functions, then you can always identify them and you can always kind of recreate their graphs. So anytime you have a degree of 2, you're going to have a perfect parabola, and it's either going to open up or down depending on if that leading coefficient, remember the leading coefficient, the thing in front of the x squared, if it's positive, it opens up. If it's negative, it opens down. And a turning point is just where it goes from decreasing to increasing or increasing to decreasing. And in this case, our turning points are minimums or maximums. And we'll either have 0, 1, or 2 intercepts, because it either will be like above the x-axis and never cross it, or in this case below. It'll touch it at its vertex, or it'll cross somewhere through it, and you get 2. If you have degree 3, right, it looks like any of these things, basic lightning bolts, and you're going to have either 0 or 2 turning points, right? Because if you're doing this, it's just always increasing or always decreasing. But if you have more of a curve to it, it increases, then it decreases, then it increases, right? So it'll either have 0 or 2. And then as far as its intercept are concerned, again, if you draw straight horizontal lines through these things, you'll see that the ones on the left only touch in one place. The ones on the right can touch in 3 places if you go through the middle, can touch in 2 places if you hit a vertex, right? So that's where you get 1, 2, or 3. And then you get to degree 4, and look what happens. You get 1 turning point, or you get 3 turning points, and you get 0 up to 4 intercepts. So you can see that the pattern is going to hold that whatever the degree of the polynomial function is, that's the maximum number of intercepts you're going to have. So you'll always have from 0 up to n many intercepts depending on the degree of your polynomial. You could also figure out your turning point. It's always going to be up to n minus 1, right? So if we're given this function here, we can see it's a power of 4, so it lives in this family. We know that we're either going to have 1 or 3 turning points, and we know we're going to have anywhere between 0 and 4 intercepts. The only way to figure all that out would be to graph it or to use some more advanced like calculus type things. If you graph it, you see you get something like this. You'd have to like zoom in and really see what's happening. So we zoom in and we go, oh, look at that. It's touching in 3 places, 1, 2, 3. And it really makes sense because this one would be really easy to set equal to 0 and solve, right? So if we take x to the 4th minus 2x squared, set it equal to 0, first thing we do is we factor out what we can factor out, which is an x squared, which leaves us with x squared minus 2 equals 0. Either this equals 0 or this equals 0. Well, if x squared equals 0, that means x equals 0. If this equals 0, we get x squared equals 2. And when you take the square root of it, you get x equals plus and minus the square root of 2. So there are our 2 zeros, plus and minus the square root of 2, which is like 1.4 something. You can see it's in between 1 and 2. And then here's the one that hits at x equals 0, right? So you can find zeros for a lot of them that are, basic-ish. Okay, rational functions are a fancy word for saying a function where you have powers of x in the bottom of a fraction. So we start with the most basic one. It's called the reciprocal function because this is the reciprocal of x. It's 1 over x. The reciprocal of something is always 1 over it. And this one graphs very easily as these two kind of like boomerang-looking things. It has a vertical asymptote at x equals 0 because obviously x cannot equal 0 because you can never divide by 0. And as x gets super, super large, right, as x gets bigger and bigger and bigger, it will never actually get to 0 because no matter how big this number is, 1 divided by it is still bigger than 0. And same thing in the negative direction, right? It's just going to be a negative number getting really, really close to 0. So these have a vertical asymptote and they have a horizontal asymptote, something that it never crosses. The more generic form of a rational function is we just say it's a function of x over some other function of x. So now we can have x's on the top and x's on the bottom. Again, the only rule being that the bottom cannot be 0. So now if we have a function of x, it's this whole darn thing can't be 0. So for instance, if the bottom of the function right? If we had, we just had f of x on top. We don't know what that is. But let's say the bottom was x squared minus 4. Well, then x squared minus 4 can't equal 0. And if you solve this for 0, you get x squared equals 4, x equals plus and minus 2. So that just means that with this function, it's not going to be defined at plus and minus 2. So when we're out here at 2, dot, 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 we're going to have a little asymptote. And out here, dot, 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 we're going to have an asymptote. And our function's going to do something like this or like this at each of these asymptotes because it'll get really close, but it can't be defined there. Excuse me. Which brings us to talking about asymptotes officially, right? I've mentioned them informally with a lot of these examples, but now let's talk about them. A vertical asymptote is a line that the function can never cross. And what happens at a vertical asymptote is your function gets super, super big on one side and usually super, super large on the other. Sometimes it'll get super, super big on both. Basically, it'll blow up to positive infinity or down to negative infinity. And they can both go to positive infinity on both sides of the line. They can both go to negative infinity on both sides of the line, or they can, do one or the other. So it's all over the place. But you just know that as you approach a vertical asymptote, your function is going to go all the way down to negative infinity or all the way up to positive infinity. So it's going to blow up and get super huge or go down and get super, super small. Horizontal asymptotes act slightly differently. Sometimes a horizontal asymptote is something that the function will never cross. But you can have functions that cross horizontal asymptotes close to the origin. But once you get further out to the left and the right? So once you get way out to large values of x on the right-hand side and way, way out to super small values of x on the left-hand side, like negative 1,000 and positive 1,000, those kinds of things, then the function will always settle down and it will remain on one side of that horizontal asymptote. It might cross it a bunch in the middle, close to 0 for small values of x. It can bounce back and forth all over the asymptote. But as your x's go out to the extremes, it will always level off and then stay on one side, either above or below. There's some very rare ones that continue to bounce back and forth, these oscillating ones. But then as it gets out, it really levels off at that number. So that's what asymptotes are, right? And to figure out how to find them, you're basically vertical asymptotes, you're just figuring out when the function is undefined. And for horizontal asymptotes, really what you're doing is you're taking limits as x goes to infinity and x goes to negative infinity, and then asking yourself what happens to the y values. So it's kind of and there's some different tricks you have to do for that. So if we just take some values from -5 to 5 and start plugging them in, we can get an idea of what the thing looks like, and then we can start graphing it, right? So here are all of our values plugged into these functions, this rational function. And here are all the values you get. You can see that starting at -5, we're 2, then we get a little smaller, a little smaller, a little smaller. We keep getting smaller, right? And then all of a sudden we go down into the negatives, right? Smaller, 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 smaller. And then all of a sudden it jumps up to a huge positive number and then gets smaller, smaller, smaller. So that's weird. We have a function that basically starts, at 2 and kind of goes down and starts to go down quickly, right? So it even kind of looks like this, even more extreme. And then it gets to a certain point, and all of a sudden it's way the heck up here at a positive number, and then it starts coming down again. So what does that make you think it's going to look like, right? We're going to have some sort of asymptote in between these two, and probably a horizontal one as well. It's probably going to look pretty similar to that original function. And sure, it should, because they're all part of the same family, so they're all going to have relatively the same shape. Now, if we want to figure out what happens at the extremes, we do that. We plug in extreme values, and we see what happens. If we go way out to a negative number, we see that our y value is getting closer and closer to 4 from below. And we go way out in the other direction, it's getting closer and closer to 4 from above. So now we put all this together and we go, well, hey, that means we must have a horizontal asymptote at 4. And this one's getting closer and closer from above. This one's getting closer and closer from below. And then we saw that in our table, the jump happened between 2.9 and 3.1. So it happened at 3. And in fact, if you look at the bottom of the function, 3x minus 9, and you set that equal to 0, 3x equals 9, x equals 3, which is what we did up here, and I kind of glossed over it because I didn't want to give it away right off the bat. You can see that x equals 3 is not in the domain of our function. We can't let x equal 3, otherwise we're dividing by 0. So that's why we have a vertical asymptote at 3. And by plugging in numbers close to 3, right, we can see what happens. So as we get close to 3, as we come down from big numbers and get closer to 3 from the right-hand side, we can see that it gets super big, so it blows up to infinity. As we get closer and closer to 3 from the left side, right, so we come at it from smaller numbers, it goes down to really super large negative numbers, right? So that's why we know that it goes down here and it goes up there, and we basically have the same kind of shape that's just been shifted a little bit. And those are our asymptotes, right? So vertical asymptotes happen whenever the bottom equals 0, and horizontal asymptotes happen based on the powers of the top and bottom. And books like to give you all these silly rules that you're supposed to memorize, that when the degree of the top is this and the degree of the bottom is this, then we get this type of asymptote and blah, 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 blah. You can memorize those if you'd like. But I always like to say it's much easier to just think your way through what happens depending on what the powers are. Okay, so if the two powers are the same, so let me just, let's get a new slide in here. Okay, so let's look at the cases. There are really only 3 cases. So case 1, the degrees are the same, right? So they talk about the top degree being n and the bottom degree being n. So we can just say n equals m, which means you have the same degree, like something like 3x to the 5th plus blah, 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 all over 2x to the 5th plus blah, 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 blah. Well, when we're looking at horizontal asymptotes, we only care what happens at the extremes, right? So way out there for large values of x, or way to the left for really, really large negative values, right? And when you put really, really large values into powers, they get bigger even faster. And so what happens is, even if the next thing was like 1,000 x to the 4th, as soon as x is 10, 100, right? If x is 100, you get 100 to the 5th, which is 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, right? So that's what that number is. And then you put 100 to the 4th, which is 8 zeros, plus 3 more, gives you 11 zeros. So this one's going to be bigger. Then you go one more, right? And this is going to get bigger. So basically what's going to happen is eventually this number is going to get so much bigger than this number that the rest of this stuff is inconsequential. It doesn't do anything. And the basic shape of this function just morphs into the 2 leading terms. So if I've got 3x to the 5th over 2x to the 5th, that obviously cancels to just 3 halves. So what that means is my horizontal asymptote is going to be the line y equals 3 halves. It's just going to be a horizontal line up there at 3 halves. Because as x gets super, super large, the function is going to level off. And as it gets super, super large in the other direction, it's going to level off either below or above it. I don't want to, take the time to figure out if it's above or below, but you get the idea. That's case 1. Case 2. N equals m plus 1. So the top is just 1 bigger than the bottom. So again, we can do 3x to the 6th now over 2x to the 5th, and then plus all this junk, which remember, doesn't matter because it's all going to cancel out when we have really, really big numbers. And then we're left with this, and if we do the math again and do the simple reduction, we just get 3 halves x. So if we graph 3 halves x, well, guess what? That's a straight line with a slope of 3 halves. So that means we're going to have what's called a slant asymptote, and at the very end, our functions are just going to head off to infinity along that line. Then the third version is that n is less than m, right? So remember, n is the one on top, and m is the one on bottom, right? So if n equals m plus 1, it's just one bigger than the bottom. So here now n is smaller than the top. So now we have 3x to the 5th over 2x to the 6th, plus blah, 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 plus blah, blah, blah. Well, now when you reduce it, you're left with 3 over 2x, right? And in fact, if this was even bigger, if this was 7, it'd be squared. If this was to the 8th, it'd be cubed, right? Doesn't matter what power of x is, the answer is still the same, that as x gets super, super large, this fraction gets super, super small, and you're going to have a horizontal asymptote at y equals 0, right? Because it's just going to get closer and closer to 0. It'll never hit 0 because it'll be 3 divided by some huge, huge number, but you get a horizontal asymptote at 0. So those are your 3 cases, your only 3 cases, and you can memorize them, right? The book will tell you, hey, if n equals m, this is what happens. If n is greater than m, this is what happens, and so on and so forth. But I think it's easier to just kind of think about it conceptually and go from there. All right, how about total costs and average costs? So if we have a cost function, the average cost is just total cost divided by a unit, right? Because it's basically cost per unit. Per always means division, so cost per unit. All we have to do is divide by x. Then we get this bad boy. Then we graph it, and we get this funny thing. And we can find that function by, using a graphing tool or whatever. We know that it's undefined at 0, so this is going to have a vertical asymptote at 0. And then if we look at the rest of it, we see that as x gets really, really large, this just becomes like nothing, right? As this gets really, really large, this goes to 0, and then the function just looks like 3 plus x. So that's why we get this straight line that just looks like a straight line with a slope of 1. And that's all that we're talking about here. We can see that the minimum average cost, right, is going to be down here. And we can figure out what that is. It looks like it's going to be about 60 something, and it ends up being 63. To find that with this function, we don't have the tools to do that. We would have to do that with some calculus. Okay, the last one we're going to talk about, piecewise defined functions. These are just functions that are defined by multiple rules, and those rules just take effect for different values of x. So different parts of the function will act differently. The absolute value function is one of those. We know what an absolute value function looks like, but technically it's defined as the function, the absolute value function just gives you the number that you put into it whenever x is greater than or equal to 0, but it gives you the opposite number when it's less than 0. So here it is, when it's 0 or greater, you just get the function y equals x. When it's less than, you get y equals negative x, and when you put them together, you get that little v that we all know is an absolute value function. But we can have piecewise defined functions that aren't defined so uniformly. And it basically just says our function behaves like this when x is between these numbers, then it behaves like this when it's between these numbers, and then it behaves like this when it's greater than that number. So you're basically just going to take your graph and you're going to break it into 3 pieces. You're going to have the piece that goes from 0 to 100, then 100 to 500, then 500 and above. And you're just going to graph these 3 functions in each of those spots and see what it looks like. Now, if you don't need to graph it, you just need to evaluate it, well, it's really simple. If you want to know what the monthly charge for 1100 kilowatts is, well, 1100 kilowatts, right, happens over 500. Because this is a charge in dollars for x kilowatts. So x equals number of kilowatts. Like if they said x is 100 kilowatts, right, then 11 would be in here. But x is just number of kilowatts. So for 1100, we use the last one, and we'd plug 1100 into this function to get our answer. If we want to know 450, well, 450 is between 100 and 500. So we would plug 450 into the second one. And that's how we would get those 2 answers. So that's how piecewise functions work. Okay. That's everything for this one.